Today we're going to be talking about something called cofunctions. And in order to explain what cofunctions are, we're going to start with a couple of examples. The first one talks about us having a right triangle, ABC, which you can see is shown in the picture. And the measurement of acute angle A is denoted by the symbol alpha, which you may or may not have seen before. And the measure of the acute angle B is defined by beta. So that's what those symbols are. That's what they are called, in case you see them. It says determine the values in the table based on this triangle of the sine of alpha. So if I take a look for sine of alpha, I know that sine alpha is opposite over hypotenuse. So here's angle alpha, here's the opposite, here's the hypotenuse, which gives me that it's equal to A over C. If we had numbers for A and C, we would of course put those in there, but we don't have them. I'm also going to move on now and talk about the cosine of alpha, which is here, since I'm already looking at angle A. So when I do the cosine of alpha, it's the adjacent over that hypotenuse. So cosine of alpha is equal to B over C, adjacent over hypotenuse. And then I'm going to switch, and now I'm going to go on to talking about angle beta. And for angle beta, which we have up here, this is the opposite, this is the adjacent, and this is the hypotenuse. So the sine of beta, opposite over hypotenuse, is B over C. And the cosine of beta, which is adjacent over hypotenuse, is A over C. From this table, they want you to notice something. What they want you to notice in this table is that when you do the sine of alpha, it is equal to the cosine of beta. So they want you to notice that the sine of alpha is equal to the cosine of beta. They also want you to notice that the sine of beta is equal to the cosine of alpha. So sine of beta equals the cosine of alpha. So there's two things that you notice when you go through and do this. Now, in this case, you can see that they both deal with sine and cosine, and then there's these two angle measures, alpha and beta, that occur in both of these. The alpha and the beta that occur in both of these, we do have a little bit of information about. We know that in our triangle, we have alpha plus beta plus angle C equals 180, because all of the angles add up to 180. We also know that angle C is 90 degrees because they tell us that this is a right triangle. If I subtract 90 from both sides, I find out that alpha plus beta have to add to 90 degrees. So in other words, angle alpha and angle beta have a sum of 90 degrees. Therefore, they are called complementary angles, a word that you've heard numerous times in the past. Same thing over here. Beta plus alpha, those two angles have a sum equal to 90 degrees. They are complementary as well. As we move on to question number 1, it says, take a look at the right triangle ABC, where angle C is the right angle, and the measures of angle A and angle B are alpha plus beta respectively. Based on the fact that we are looking at this in this particular way, if we're talking about adding alpha plus beta, it's the same scenario that we had in the last one. So alpha plus beta has to equal 90 degrees because the other angle in the triangle we already know is 90, which will give us 180 total. It says use the trig ratios to describe BC, which is here, over AB, which is here, in two different ways. One of the ways that I can describe it is if I focus on angle alpha, this is the opposite and this is the hypotenuse. So one of the things that I know is that BC over AB is equal to the sine of alpha. It's equal to opposite over hypotenuse. And then if I change now, and I look at angle beta, this is my adjacent and hypotenuse. So that means that I know that BC over AB is equal to cosine of beta, adjacent over hypotenuse. And then they ask us to do the same thing. This time, however, they asked us to do the same thing using AC and AB. So I'm going to go back now and erase what I have in my picture and color code it again. So in here, they're talking about AC and AB. With respect to angle alpha, this is adjacent and hypotenuse. So AC over AB must be equal to the cosine of alpha. One more time, applying the same idea here. With respect to angle beta, this is the opposite in the hypotenuse. So that means that if I have AC over AB, that is equal to the sine of beta. And once again, we can see that we have that same relationship that we had in the last section, where the sine of alpha equals the cosine of beta, and the cosine of alpha equals the sine of beta. So when they say, what can you conclude? We'll look at the first one here. That's what goes with part D. We can say that the sine of alpha is equal to the cosine of beta if alpha plus beta equals 90. So this rule only works if those two angles are complementary. And then it asks me in the next section what I can conclude about cosine alpha and sine beta, which we did in part C, and we can conclude that cosine alpha is equal to the sine of beta. And again, that is if we know that alpha plus beta is equal to 90 degrees. So that being said, if we're looking at examples in number 2, we are allowed to say that these sine and cosine values are equal if we know that our alpha plus our beta is equal to 90 degrees. So in this case, if theta, our alpha value, plus 25 equals 90, we can go through and solve and find out that theta is 65, and the value of theta of 65 makes that equation equal. If you wanted to go through and do a check for that, just to know if what you did is right, that means that when you type sine 65 on your calculator, when you sub 65 in for theta, you should get the same exact value as when you type in cosine 25 on your calculator. So that will check. As I move along to each of these questions, they're all going to be the same idea, where I want to go through and prove that the sine and cosine values will be equal when the value of alpha plus beta equals 90. So for question number 2, it will be true when theta is 10. Part C, I'm going to do the same thing. I'm taking the two angle measures and I'm adding them to 90 because it will be true that the sine value and cosine value will be equal when the angles are complementary. So this is 2 theta. You treat the thetas like an x, plus 10 equals 90, which means that 2 theta equals 80 when I minus 10 from both sides, which means that theta is 40. So again, theta is the variable for the angle. Sometimes there's an x in there, sometimes there's a theta, sometimes there's an alpha, sometimes there's a beta. So we just treat the theta as another variable. In the next one, those two will be equal if theta minus 45 plus theta equals 90. So that is if 2 theta equals 135, which when I go through and solve shows divide by 2 that theta is equal to 67.5. It says in question number 3, for what angle measurement must sine and cosine have the same value? The reason that I would know what I'm going to know is that if I am taking the sine of something and the cosine of something, and I want them to be equal, what that means is the sine of the angle is going to be equal to the cosine of the angle. It means that I know that the two thetas, basically the alpha plus beta values, have to add to 90, which gives me that 2 theta equals 90, which then of course means that theta is 45. So when theta is 45, the sine and cosine of each of those will be equal to each other. Sine 45 equals cosine 45. In part 4, they're asking us what is happening to the A and B values as theta changes. So I'm going to draw a couple of examples in here so you can see what it is that they're asking exactly, because I think kind of it might be a little bit difficult to tell. So you can see for the first example, this is what theta is. Here's our A, and here's our B. If I change the angle measure, so I go back and I say, you know what, I'm going to, in this case, make theta be a little smaller, and I draw it like this, and my theta is now here. Here's my A value, and here's my B value. So if theta gets smaller, A gets smaller, and the B value gets larger. And you can see that that's the case. If I compare the green side length of A to the pink one, A is shorter. If I compare the green side length of B to the pink one, the B is longer. So I'm going to do the same thing now, except this time when I go in here, I am going to draw my theta bigger. So in other words, I'm going to make the theta be right here where it's this whole big angle. You can see in that case that now your side length of A, which is right here, compared to the pink one, is much larger, but the side length of B compared to the pink one is much smaller. So I'm going to summarize that by saying that if the theta gets larger, A gets larger, and B gets smaller. It then asks us what's happening here with respect to sine and cosine. So it's asking us this question with respect to sine and cosine. What you want to keep in mind when you go through and do this is if we're looking at the green triangle, so I'll go back and kind of color code this. If we're looking at the green triangle and we're making our sine value change, our value for sine in the green one is A over this measurement right here, which is C. And we can see that our A value gets smaller, but the C value stays the same. So this is A over C. And because the C value stays the same in either triangle, every single one of these C's is the same measurement. This C, and this C, and this C. Therefore, our denominator is not changing. So if we make the a value smaller over the same denominator, that's going to mean that the value of sine is getting smaller too. If I look at cosine under the green triangle, and I see that cosine is adjacent side of b over hypotenuse of c, and b is getting larger compared to the pink one while c stays the same, it means that the cosine value will get larger. If I go back now and I compare the orange triangle, which means I'm using this information right here, in this particular case, if I'm looking at the orange triangle, the A side is much bigger than the pink A. So when I'm comparing the sine and doing opposite over hypotenuse, so I'm doing A over C, the C value stays the same for every triangle. So if the A got bigger over that same denominator, it means that cosine got larger. And if I do the cosine of theta, which is B over C, compare the B value of the orange triangle to the pink one, and that got smaller while the denominator stayed the same, then that means the value of cosine got smaller. So basically, they're trying to get you to notice that if your angle gets smaller, sine will get smaller, cosine will get larger. The bigger that your angle gets, the larger cosine is, but the larger sine is, but the smaller cosine is. So there's a direct relationship between the size of the angle and the relationship between sine and cosine. In the question at the bottom, they're asking for us to go through and find the exact values of sine, cosine, and cosine for 0, 30, 45, 60, and 90. You could, if you wanted to, go through and look at 30, 60, 90 triangles and 45, 45, 90 triangles to help you with some of this information. So I will write that in here quickly. We know that if this is a 30, 60, 90 triangle, if this side is 1, this is the 2a side, so it's 2, and this is the a radical 3 side, which is going to be 1 radical 3 or radical 3. And in our 45, 45, 90, if this side is 1, so is this one, which means this will be radical 2, or 1 radical 2. So we could use this information to fill in our chart, and I'll show you how that works. If we're doing the sine of a 30-degree angle, I know that for the sine of a 30-degree angle, here's my 30-degree angle. It's opposite over hypotenuse, so it's 1/2. For the sine of a 45-degree angle, it's opposite over hypotenuse, so it's 1 over radical 2, which, don't forget, you need to rationalize, which gives you radical 2 over 2. And you could work your way through on all of these and figure out what they were. Notice that the directions say that you're supposed to have quick recall with these. I will tell you that I don't generally go back to my triangles to figure this out. I just know these values because of that quick recall. And you are essentially supposed to know them as well. The second row, which deals with all cosine, is essentially this whole top row picked up and put in the backwards order. So sine and cosine are the opposites of each other. They're the cofunctions of each other, if you want to call it that. I'll point out to you what it is that I mean. In other words, we've already talked about how if we know the sine of 30 is a cofunction with the cosine of an angle, we know it has to be equal to the cosine of 60 because we've talked previously today about how the sine of 30 is equal to the cosine of 60. These angles, in order for the sine and cosine values to be equal, those angles have to be complementary. Sine and cosine are the cofunctions, and they will be equal if the angles add to 90. In the part B question, they're telling us that we have an equilateral triangle and each of the sides is 2. It tells us that D is the midpoint of side AC. So that's a midpoint, so that means that these two are equal to each other. It asks us to label all the side lengths and angle measures for this triangle. And we're supposed to use our figure to determine the sine and cosine of 30 and 60 degrees. So in this, if our triangle is equilateral, it also means that it's equiangular, which means that all of the angles are 60 degrees. If D is the midpoint, then I should be able to draw in from the top angle an altitude that goes down to point D. Altitudes by definition hit the opposite side of the perpendicular, therefore I have a right angle there. The altitude drawn in an equilateral triangle is also the angle bisector, so that means that up here at the top, I know that each of these angles is 30. If the whole thing is 60, each angle is 30. So right now, if I focus on my right triangle that's on the right-hand side, which is right here, I essentially have a 30, 60, 90 triangle. So here's 30, 60, 90, and I know that this side is 2. Remember that that is the 2A side, which means A is 1, and then the side that's across from the 60 is the A radical 3 side, which is 1 radical 3 or just radical 3 to make things simpler. It asks us to find all the side lengths and all the angle measures. So if I take a look at the original triangle, I have all the angle measures drawn in, and I have all the side lengths drawn in. I could label that this altitude is radical 3, and each of these two sections along the bottom is 1, if I wanted to get all the information out of that. And they're asking me to use my figure to determine the sine and cosine of 30 and 60. So I'm going to do sine 30, cosine 30, and I'm also going to do sine 60, and I'm going to do cosine 60. So if I'm focusing on my 30-degree angle to start with, this is the side opposite, this is the side adjacent, and this is the hypotenuse. So sine of 30, opposite over hypotenuse, 1/2. Cosine of 30, adjacent over hypotenuse, so radical 3 over 2. I'm going to flip now over to the 60-degree angle, and while I'm looking at the 60-degree angle, this becomes my opposite, this becomes my adjacent, and my hypotenuse stays the same. So sine of 60, opposite over hypotenuse, radical 3 over 2. Any thought on the fact that these two should have turned out to be equal? Probably, because they're cofunctions. We have sine and cosine of two angles that add up to 90. Using either your triangle or the cofunction idea, you should be able to find out that the cosine of 60 is 1/2. In my picture, it's adjacent over hypotenuse, or I can use the cofunction rule that says if it's the sine of 30, it must be equal to the cosine of 60. For question C, it says draw an isosceles triangle with length 1. It's already drawn for us. I'm just going to label this as a length 1. It says, what are the measures of the acute angles? The two acute angles that are here and here are both 45 degrees because we know the triangle is isosceles, and if the two sides are the same, the opposite angles must be. And if angle B is already a 90-degree angle, we have 90 degrees to split evenly between angles A and C. It says, what is the length of the hypotenuse? So the length of the hypotenuse, if we use the special right triangles, is the A radical 2 side, which is 1 radical 2, which is just radical 2. It says use your triangle to determine a sine and cosine of the acute angles. So I'm essentially looking at the sine of 45 and the cosine of 45. I only need to do one of the angles because they're equal. If I do sine of 45, this is the opposite over the hypotenuse. So this is 1 over radical 2, which we then, of course, must rationalize. So radical 2 over 2. And then the cosine of 45, same exact thing. I have adjacent over hypotenuse, which of course needs to get rationalized as well. Notice these are equal, which is exactly what we predicted to happen on the previous page. If it's the sine and cosine of 45, their answers for sine 45 and cosine 45 must be equal. For question number 5, it says find the missing side lengths of the triangle. I'm being asked to find both side A and side B. So with respect to my 30-degree angle, this is the opposite in the hypotenuse and the adjacent. If I'm finding the missing side length A, I'm going to do the sine of 30 equals A over 3. So A equals 3 sine 30, which means that A is equal to 1.5. If I'm looking for B, side B, now I'm looking at the adjacent side, which I'm going to compare to the hypotenuse, therefore cosine. So cosine of 30 equals B over 3. And B is equal to 3 cosine 30 when I cross multiply, which means that B is equal to, when I type that in, big decimal here, I'm not going to do question 6 with you because it's very similar to question 5, and I know this video is already a little bit long. If you would like to do question 6, just to make sure you can get the correct answer, the answer for C is that, and the answer for A is this. So you can try these on your own. See if you can get those right answers, and if you have questions, I will answer them tomorrow in class.